Good morning to one and all. This is Ram Babu, lecturer in chemistry, Government Degree College, Perumalpuram, East Godavari District, Andhra Pradesh. Now, I am discussing about D block elements. This is regarding to BSc third semester syllabus. So now, what are the D block elements? As for the definition, so the D block elements have been defined as the elements in which the last entering electron or the differentiating electron entered into the D subshell or penultimate shell or n minus 1 shell. So those particular elements are nothing but the D block elements. And one more point here it is, the D block elements are also called the transition elements because so they exhibit the gradual transitional behavior between the highly reactive S block elements and the P block elements in their properties. That is their properties have been found to be intermediate between those of S and P block elements. So that's why these particular D block elements are called transition elements. And in the long form of the periodic table, so the D block elements are placed in between the S and P block elements. And now we are going to the classification of D block elements. So the D block elements are classified into four four transition series. First one is first transition series, that is called 3D transition series. Here in these particular elements, the differentiating electron, that is the last entering electron, is entered into 3D subshell. So these elements are coming from the scandium, whose atomic number is 21, to zinc, so that is with atomic number 30. And the second transition series is, this is also called the 4D transition series. So in these elements, so the differentiating electron is entered into the 4D subshell. So these elements consist of from the yttrium, that is atomic number 39, to cadmium, whose atomic number is 48. Similarly, the 3D transition series or third transition series or the 5D transition series, so the elements are from lanthanum, whose atomic number is 51, and hafnium, that is atomic number 72, to mercury, atomic number 80. And the last and final one, that is the fourth transition series or the 6D transition series. This is the incomplete series, and the main elements regarding this particular 6D series are the actinium, whose atomic number is 89, and then the rutherfordium, and some the elements are present here. And all of these particular elements are radioactive and do not occur in nature. These have been artificially made in the laboratory. That is the most important point here. And then we are going to the general characteristics of the D block elements or the transition elements is they forms most of the transition elements forms the stable complex compounds like the potassium ferrocyanide, hexamine cobalt 3 chloride, like that. So they can forms the stable complexes, and they have the high melting and boiling points because they are having the good metallic properties, and more because of those properties they having high melting and boiling points. By using the free electron theory or the valency bond theory or band theory, suggested that the metallic species having the higher melting and boiling points, they can contain the large charge by radius ratio, and they forms the compounds which are the paramagnetic in nature. Majorly most of those particular D block elements forms the paramagnetic compounds, because so in those particular transition elements, so the partially filled d orbitals are present. They are hard and possess the high densities, and their compounds have the catalytic properties. Many of the reactions in the organic chemistry and as well as the inorganic chemistry, so many reactions can be catalyzed by these particular the compounds of the transition elements. For example, in the synthesis of in the Haber process, the synthesis of ammonia can be accomplished by the catalyst like the iron and then molybdenum, and very famous reaction that is the contact process. So the preparation of sulfuric acid can be done by using the vanadium pentoxide. Like this, so many catalysts are used, these particular transition elements. Next, they can show the very characteristic properties. So these particular transition elements can shows the variable oxidation states, and they are malleable and ductile. That means they can drawn into the thin sheets and long wires. So their compounds are colored in nature. For example, manganese sulfate, it is pink in color. So there is copper sulfate pentahydrate, that is blue in color. So all these are all compounds are colored in nature. And then the characteristic, now let us discuss so one of them one by one, these characteristic properties. There is the electronic configuration. First one is electronic configuration. So the general valence shell electronic configuration of the d block elements is n-1 d1 ns 1r0, where n-1 d stands for the inner shell's host d orbitals may have 1 to 10 electrons, and the s orbitals of the outermost shell that may have no or 0 electrons or 2 electrons. The filling of the d orbitals takes place after the s orbital of next higher shell has already filling according to Aufbau principle. So the common examples for this particular first transition, second transition, and third transition, like we can see the scandium atomic number, that is 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, 3d1. So like this, so the first element starts from the scandium 3d1 to 3d10. So this is the general electronic configuration of the transition elements. First 3d transition element. In this particular 3d transition series, so the chromium and copper shows the anomalous electronic configuration. So because of their extra stability due to the half-filled orbitals of the half-filled or full partially filled orbitals. So because of that particular stability, they can show that the anomalous property, anomalous electronic configuration. And moreover, some of the compound, the reasons for the pairing energy of the for ns electrons, and various electronic configurations are given here. And then the oxidation states here, they can show the variable oxidation states because they can show the 2 or more oxidation states. Majority of the transition elements, the energy difference between the n-1 d orbital and the ns orbital is very low. So as a result of that one, the ns electrons and the n-1 d electrons participate in the bond formation, so that they can show the different, and that means the more number of oxidation states. So here the common oxidation state in the 3D transition series is +2, and the various oxidation states of the various 3D transition series are given below. So in this particular series, we can show that the scandium shows +3, titanium +4, and vanadium +2, +3, +4, +5, chromium +2, +3, +6. Like this, they can show the different oxidation states. And then we are going to the stability of oxidation state. Here, the more stable oxidation state increases in the increasing order. That is, the 3D series having the lesser and less stability, while the 5D increasing order is the 3D is less than 4D is less than 5D. So here the 3D elements are the most stable in +2 oxidation states, and the relative stabilities of the oxidation states depends upon the many factors like the stability of the resulting orbital, that is ionization energy, electronegativity, and enthalpy of the atomization, enthalpy of hydration. So these are the different factors can influence the stability of the various oxidation states. Okay, so this is about the various oxidations, various reasons. So this is about the transition elements.